Okay, in this video I'm going to do some of the problems from section 7.1, and if you look on the assignment, some of the problems are starred. These are the ones I'm going to do or talk about. So let's go ahead and look at 6. I think I can do this. I'll do a screenshot of where's the screenshot? I guess it's here. Screen clipping, here we go. So here's the exercise here. So we're talking about rotations. R60 is a 60-degree rotation. So let's go back to the chapter and see what R60 really is. Get some context for this exercise. So here we are. And here's a picture of R60. We have a hexagon which we identify as 6 points, A, B, C, D, E, F. Now, of course, the hexagon also includes lines, but if the points go in a certain way, where the points go determines where the lines go. So here we have a hexagon. Now, if you can imagine twisting this hexagon by 60 degrees, the A goes to B, the B goes to C, the C goes to D, and so on. So before the twist, we have the A here. After the twist, the A moves up here. Before the twist, the B is here. After the twist, the B moves here. The hexagon itself looks the same. It's just that the vertices are labeled differently. So R60 is the mapping from this hexagon to this hexagon. So how do we make this work? We say that A goes to the position where B was. So we're saying that A maps to B. B maps to C, C maps to D, D maps to E, E maps to F. Now we've represented functions as a set of ordered pairs. So we can represent this function in this way. A goes to B, B goes to C, etc. Okay. So you can think of this here, it talks about relabeling, that the B has been relabeled as A, the C vertex has been relabeled as B, and so on. This mapping defines the rotation. So the question here was, if I look at this mapping, is it one-to-one and onto? Now at this point we just have a problem having to do with functions. And if you go back to the functions chapter, we addressed problems like this. So let me go ahead and clip this as well, because this here defines my mapping. Okay. All right, now from here I can look at this mapping as a set of ordered pairs and determine whether or not it's one-to-one and onto. So in fact, how do you tell whether something is one-to-one? Well, if each output comes from a unique input, then we have one-to-one. In fact, I could draw an arrow diagram, A, B, C, D, E, F. So these are the inputs, and the outputs, I can put A, B, C, D, E, F. And each input, in fact, is going to a unique output. A goes to B, B goes to C, C goes to D, D goes to E, D goes to F, F goes to A. So each output has only one arrow into it. So each output comes from only, or I can say at most, one input. Now be careful. This is what one-to-one means. You can't say each input goes to only one output. That's not one-to-one. And all functions do that. Even if I had B go to C and A goes to C, each input goes to only one output. But this is what means the function is to one-to-one. So the R60 is one-to-one. Okay, so that's the answer to my first one. A, the answer is yes. And here's the explanation. The explanation is here. Right now, second one is R60 output, is on R60 onto. Let's remember what we did in our previous, where do we do insert space? Okay, let's go down like this. Okay, so for part B, let's think about that. For part B, is R60 onto. So here I should label this as part A. In part B, you can say each output comes from at least one input. All right, if I take any output at all, there's at least one arrow that goes into there. So that means that R60 is onto. Okay, so you need to keep these notions of one-to-one and onto straight. You can see that what we learned in the previous chapter is useful for us. Now, what about part C? Is R60 a bijection? Well, if you remember, if it's one-to-one and onto, then it is definitely a bijection. So that's an automatic. Whoops, let me insert that. So I'll insert another space here. So, whoops, what happened? All right, well, we're getting a little bit. All right, so for part C, I can say R60 is one-to-one and onto, and that implies that R60 is a bijection. Okay, so when you answer these, you have to give both the answer and the reason why. I've given sufficient reason why. If you go back to the chapter, you'll find out that this is necessary and sufficient for R60 to be a bijection. All right, so that gives me problem 6. Let's look at the next problem. Next problem is problem 10. So let me go there and see what we can do with that. And I think I was only going to do certain parts of it. So let me snip it, and then we'll go back and look at the context. Okay. All right, so let me move it a little bit. Over here. And I think I was just going to talk about parts A and C. All right, so I think I need to insert a little bit of space at the bottom here. Good. All right, now, all right, so here it says, explain why A, so these are the two I'm going to do, A and C. Here's A and here's C. All right, let's think about A. Explain why 90-degree rotation, 270-degree rotation, or reflection across a diagonal are not symmetries of the rectangle ABCD. So let me go ahead and draw a rectangle here. I don't remember exactly how I labeled the vertices. I think I labeled this one A. It doesn't really matter. Now, it can be helpful for you to make a model yourself when you do rotate your model yourself. Now, suppose I do a 90-degree rotation of this. Okay, if I do a 90-degree rotation, then what's it going to look like? So if I do 90-degree rotation, then the A is going to go up top. I'm going to have a rectangle that actually looks vertical. Okay, so I would have A here, B here, C here, and D here. Okay, now, so the question is, why is this not a symmetry? Well, it's not a symmetry because you can tell something's happened to the rectangle. The rectangle is not in the same position. All right, and that means that it's not a symmetry. That's the definition of symmetry. Symmetry is some kind of movement that displaces the object, but displaces it in such a way that the object looks the same. So the rectangle, you can say it looks different. You can say is in a different position. After the 90-degree rotation. So this is one way to say it. There are a number of ways to say it, but this is one way. The idea is that the rectangle looks different after the rotation. All right, so it's not a symmetry. Okay, so that's all you have to write for A. You don't have to write a novel. That's just try to get essentially the basic idea. All right, so that's part A. Now, then here you're supposed to decide what kind of rectangles do these rotations give you symmetries. All right, and I can say similarly for 270. Let's just do explicitly the 270 and the reflection across the diagonal. So I need to insert space here. Let's see if all right, let's do that. Is it letting me do it? Let's go down a little bit. Okay, good. All right, so let's do a 270-degree rotation. So here if I have ABCD again, so I have ABCD. Now what about a 270-degree rotation? After a 270-degree rotation, what's it going to look like? Now you can think of 270 degrees, that's the same thing as, that's 270 degrees. When we talk about rotation, we're always talking about counterclockwise. And that's the same thing as minus 90, or I can say plus 90 clockwise. Right? If I turn this 3/4 of the way around, that's the same thing as turning it 1/4 of the way around the other way. All right? So the result would be that I'd still get a rectangle that looks like this, but the A has gone all the way around to the lower corner here, all right? That's the same thing as rotating 90 degrees clockwise, and then I label the other ones accordingly. This would be D, and then this would be B, and this would be C. Okay, and this says, so I can say the rectangle looks different. So it's not a symmetry. Okay, and then also if I do the flip around the corner, so if I do the flip around the diagonal, so here's A, B, C, D, and if I flip around this diagonal, well, you can make a model and figure out what happens. The A and the C are not going to move. So if you do this flip, you're going to find that, let's see, what's going to happen. Notice that when you have this long side from A to B, then when you flip this across the diagonal, this long side is going to be going down. Now this side here, this short side from A to D, when you flip it across the diagonal, the short side is going to be going horizontally. Or it's not going to be going horizontally, it's going to be going at some other angle. You're going to get something like, the A and the C are not going to move. So they're going to look like that. But the B and the D are going to be in different positions. You're going to have, sorry, that's A and C. Sorry. Okay. That's A and the C. I should leave myself a little more room. Let me move this one down a little more so I have more room. And I'll grab it and move it down. What's it doing that for? All right, well, I think this guy kind of screwed up here. Anyway, I got it, so all that ends well. All right, so here I'm going to flip. I'm not sure why it's doing that. It's not liking me today. There we are down there. All right, so this is going to be a flip around AC. All right, so as I said, A and C are going to be in the same place. But somehow this long side from A to B is going to go down, and it's going to look something like this. B is going to be down there, and the D is going to be up there. So I'm going to have D here and B here. All right, the important thing is that the AC doesn't move, but the B and the D are certainly not going to preserve this shape. So you can say the rectangle is in a different position. So it's not a symmetry. Okay, so that takes care of the second problem here in part 1. And let's see. Oh, I was going to do C also. I think I'll just say C verbally. What rotation angle does the identity symmetry correspond to? Now, what's the identity symmetry? The identity symmetry is the symmetry where the rectangle maps to itself. A, B, C, D map to the same position. And that's the same thing as 0 degrees. Okay, so you just call that 0 degrees. You could also say 360 degrees, but here it says give the easiest answer, which is 0 degrees. All right, so that's good for that section. I'll make another video for the other sections, and here we go.